Segments of chords. When two chords intersect in the interior of a circle, each chord is divided into two segments called segments of the chord, okay? So what I want you guys to do is I want you guys to label each of these segments of the chord. So, for example, EC is going to be one segment, ED will be the other segment, AE will be one segment, and EB will be the other segment. So this is actually 4 separate segments, okay? 2 blue ones and 2 red ones. Okay, Theorem 10.18 states that the segments of the chords theorem. So we have 4 segments. If 2 chords intersect in the interior of the circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Noah, what's your question? I'll go back at the end, okay? All right, so let's take a look. What this is saying is, if AB and CD are both chords and they intersect each other in the circle, if you take one segment of CD, let's say CE, and you multiply it by the other segment of that chord, ED, that will be the same exact result. That will be the same product as AE times EB. Okay? Multiplying any 2 segments of one chord will be the same as multiplying any 2 segments of the other chord, as long as those chords intersect each other. Okay? So let's take a look at this example. And someone explain to me why it wouldn't work for this example. Correct. They have to intersect. This, we wouldn't be able to apply it, first of all, because the chords don't really have any segments, right? They're just 2 solid chords. They don't intersect each other at all, okay? So the chords have to intersect, and then once they intersect, they'll be divided into 2 different segments. Each of those segments multiplied by each other will be the same for both of the chords. Okay. Before we move on, I want to go this slide, the secant segment slide, okay? So there's something called a secant segment. It's a segment that contains a chord of a circle and has exactly one endpoint outside the circle. The part of a secant segment that is outside the circle is called an external segment, okay? So there's a secant segment, which we're all familiar with secants, right? A secant is something that continues on outside the circle. It's a chord that continues on outside the circle. But it has an external part, which is what is defined here in red, okay? This red part is the external segment. And then the entire thing is called the secant segment, okay? Down below, that blue one is the tangent segment, okay? Remember, tangent segments only cross the circle at one point. Secant segments cross it twice, all right? All to the tangent segment. A tangent segment is a segment that is tangent to a circle at an endpoint. So the tangent segment technically is always external. It's always outside the circle. It never goes inside the circle, okay? This is really important when we find out about the next 2 theorems. So make sure you understand what a secant segment is versus a tangent segment, okay? Secant is both outside and inside the circle. Tangent will always be outside the circle. Okay. Way down back to Theorem 10.19, segments of secant's theorem. If 2 secant segments share the same endpoints outside a circle, then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment, okay? In other words, what I really want you guys to remember is this formula. Whole times external equals whole times external, okay? Where this is the whole and this is your external. This is your whole and this is your external. So just like there was with the two chords that intersected, right? The product of the whole times the external of each of these secant segments is going to be equal to the whole external of the other secant segment. To all the way slide, okay? This is when we have a secant segment and a tangent, okay? And the only difference is your tangent is completely external, so it's just going to be the tangent squared. Do you remember how I said it's whole times external equals whole times external? If the tangent is completely external, it's just the tangent times itself. So it's going to be the external squared. Okay? That's why it's tangent squared equals whole times external. This first example. So go all the way down to example 1, where it says find the value of x. Okay? And in this example, I want us to figure out, okay, how are we going to find x? Well, there's two chords, right? Do they intersect each other? Okay, so now we've got 4 different segments. We've got the segment 12 and 2, and we've got the segments x and 3. What should we multiply by each other?
12 by 2.
Yep, we just take 12, multiply by 2. And we take x, and we multiply it by 3. So, what's 12 times 2, peeps? 24 equals 3x. And then we just divide by 3, and you get 6 equals, I'm sorry, not 6. 8 equals x. Now, this is true for any chord, 2 chords that intersect inside the circle. So even like if you had a chord that was super small over here, it's going to divide each of those segments into 2 parts, into 4 segments, that when you multiply them together, they're going to give you the same product. Okay? All right. Go. So we're back to this slide with the examples. Let's take a look at this one, okay? So this is an example of a tangent plus a secant, okay? Remember, for a tangent and a secant, it's going to be the tangent squared equals the whole times the external. All right, guys, what is the tangent? What's the length of the tangent? Yep, it's just x. So we're going to take x squared equals, what's the whole length of the secant? 24 times, what's the external? No? Just 6, okay? So we added 18 plus 6 to give us 24, and that's the whole length of this entire side. And then the external is just this little part, which is 6. So x squared equals 24 times 6. We're going to get x squared equals 144. We take the square root of both sides, and we're going to get x squared equals, x equals 12. Okay, let's jump to the next example. Okay, this is an example of two secants. Secant and secant. Okay, when we have two secants, it's going to be whole times external equals whole times external. Okay? Let's take a look at the first line segment. What's the length of that whole thing? 12. What's the length of the external part? 4. So 12 times 4 equals, let's take a look at the second one. Now, be careful here. What's the length of the entire segment? X plus 6. And what's the length of just the external part? Just 6. So we multiply it by 6. If we multiply this out, we're going to get 48 equals 6x plus 36. We distribute that 6 to both terms. We subtract 36 from both sides. We're going to get 12 equals 6x. Divide by 6, divide by 6, and you get 2 equals x. Okay, let's check out another example. Okay, what kind of example is this? Two secants, a secant and a tangent. What's going on here? It's a secant and a tangent. Yep. Okay, so remember, we're going to take the tangent and do what with it? What do we multiply the tangent by? Yep. So what's the whole thing for this 10? It's just 10, right? What's the external part? It's also 10, okay? Do you see how the whole and the external for a tangent is going to be the same? Okay? So this tangent just gets squared because we multiply it by itself. Now the whole of this portion is what? Good. 2x plus x. And we multiply that by the external part. What's the external part? X. Yep. So our tangent, which is 10, we square it, equals 2 plus x is just 3x times x. We're going to get 100 equals 3x squared. And now we just have to solve. What would we do to solve this, peeps? A little bit of algebra.
The x alone.
Yep. How do we do that?
Divide x squared by both sides, or multiply.
Divide by 3 and then square it?
Yeah, let's divide by 3 first. So when we divide by 3, let's just leave this as 100 over 3 equals x squared. And then we don't square it to get rid of the squared. What do we do?
Get the square root?
There we go. We take the square root of both sides, and then we're going to just get 10 over the square root of 3 equals x. Because that's the square root of 100, which is just 10 over the square root of 3.